Ionization energy is the amount of energy needed to ionize an atom, and that ionizing is talking about turning something from an atom into a positive one ion. So we talk about the ionization energy being the amount of energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms. That's the sort of standard definition for ionization energy. By removing an electron or a mole of electrons, we're going to be left with positive ions. So we can always write an equation for ionization energy by doing 1 mole of whatever it is we have, and we have to have gaseous atoms, so we have 1 mole of that, and it's being turned into 1 mole of gaseous 1+ ions with electrons being removed. So this is the first ionization energy of something. Another thing to think about is what then the second and third ionization or successive ionization energy equations would be. So this is something that people often get a bit confused about. Each time we're doing a successive ionization energy, we're just removing 1 mole of electrons from the previous one. So with a second ionization energy, we want to start with the positive 1 ion, so 1 mole of gaseous positive ions, and it's going to make 1 mole of gaseous 2+ ions plus 1 mole of electrons. So don't make the mistake of going from the atom to the 2+ ions straight and removing 2 electrons. Each time we're just removing 1 mole of electrons. So whether or not it takes more or less energy to remove that mole of electrons is all to do with how strongly the nucleus in the atom is attracting the electron or the outer electron. And that first ionization energy is always going to be talking about how much energy it takes to remove that outermost electron. So as you go down a group, we're going out in these electron shells or up in energy level. So the electron from, let's say this is the electron in the outer shell, as we go down a group, the electron is further away from the nucleus, which we call atomic radius. Okay, so it has a larger atomic radius because the outer electron is further away. So this distance from the nucleus to the outer electron is higher. There's also more shells, and more shells will mean more shielding. And shielding is the effect that complete shells of electrons have. So the complete shells inside here, so let's maybe highlight that with a colour. So these complete shells will shield the attractive effect of the nucleus for the outer electron, let's say here. So the more shells there are in between the nucleus and the outer electron, the more shielding there will be. And both of these things, increasing atomic radius and more shells and therefore more shielding, will mean a weaker nuclear attraction. Okay, and a weaker nuclear attraction will mean a lower ionization energy because there's going to be less energy needed to remove something that has a weak attraction. Okay, the other thing to consider when we're talking about ionization energy and trends in ionization energy is the nuclear charge, which is all to do with how many protons you have. So nuclear charge, this basically means what's the charge in the nucleus, and that's dictated by how many protons are in the nucleus. So in this situation, going down the group, the nuclear charge is actually increasing, and an increased nuclear charge will mean a higher nuclear attraction and therefore higher ionization energy. But in this case, going down the group, the effect of the atomic radius and the shielding outweighs the effect of the nuclear charge. So these two would cause a reduction in the ionization energy. This one would cause an increase in the ionization energy. But in this case, when we're going down a group, these two factors outweigh, or they're more important than the nuclear charge effect. But these three factors are always the same factors that we want to consider when we're discussing the trends in ionization energy. So, for example, you might be asked about how the ionization energy first ionization energy changes as you go across a period. And for that, because we're in the same shell going across a period, there'll be the same amount of shielding. So there's no change or effect from the different amount of shielding, or at least in general overall. However, there's an increased nuclear charge because as you go along, there's one more proton in the nucleus as you go along. So that's going to be an increasing charge from the nucleus and therefore stronger attraction. So the stronger attraction will mean an increased ionization energy. So increased nuclear charge as we go across the period, and so a stronger ionization energy. In terms of atomic radius, this one is a little bit counterintuitive, but because of the increased nuclear charge, but being in the same shell, the electrons get pulled slightly closer together. So the atomic radius slightly decreases, and the number of shells stays the same. So going across the period, in general, we expect there to be an increase in ionization energy due to the increase in nuclear charge, because there's a relatively small effect from the decrease in atomic radius and the number of shells is the same, so the amount of shielding is the same. However, there are a couple of exceptions to this, and you might sometimes see a graph that looks, I'll just do a quick sketch of it. It looks something like this. So it's just a sketch, it's not to scale, but this would perhaps represent the elements in period 3, and we would expect there to be a general increase in ionization energy, first ionization energy. However, there are these kind of anomalies that we wouldn't necessarily expect. So this is atomic number here. And that's because of subshells. And so ionization energy, the reason we learn about ionization energy is because it gives us evidence for the presence of subshells. So going from the first element in a period to the second element, both of these electrons are in the S subshell. But this third one here is now in a new subshell. It's in the P subshell. Okay, and so this S subshell has a mini shielding effect on the P subshell. So basically those, even though it's not a full shell, the complete subshell has an effect of shielding this P electron from the nuclear attraction, and that means that this first P electron here is easier to remove than you might expect it to be. This second one here is another electron in another p orbital. So you may remember there's 3 p orbitals. That means a total of 6 electrons that are possible to have in the p subshell. So each time as we go across the period, this is the first electron in the p subshell, this is the second, this is the third, and we fill orbitals one at a time so that we're not adding 2 orbitals to one and then we don't have in the other. It's a more stable configuration because if you put 2 electrons into one orbital, they will repel each other. So as you do this continues with the normal pattern that we would expect, but when we get to this one here, so this jump here, it's again lower than expected, and this is because of something called spin pair repulsion. So this electron here is going to be coming into the second electron coming into that first p orbital. And because these electrons are in the same orbital, these electrons repel each other. And so this is called spin pair repulsion. Okay, so spin pair repulsion means that this greenish, if you can see the difference in color, this second electron here is going to be much easier to remove than expected because the other electron that's already in the orbital is going to be repelling it. Then as we continue, we have the same kind of pattern with increasing ionization energy with nuclear charge. The other evidence for shells is when you have successive ionization energies. So for successive ionization energies, we normally have the number of electrons removed, over here, and then this is the ionization energy, or the amount of energy needed to remove that electron. So this is often used to show, again, this was evidence that shells exist. So if we've taken the example of sodium, for example, sodium has an atomic number of 11, and we might be able to, from GCSE, say that that's going to have an electron configuration of 2, 8, 1. So that's 2 in the inner shell, then 8 in the next shell out, and then 1 in that outer shell. So if you do the successive ionization energies for sodium, we're talking about the first, then the second, then the third, then the fourth ionization energy, etc. It's going to always get harder to remove the next electron, because each time we're removing an electron from an already positive atom, and each time that atom is getting, or that ion is getting, more and more positive, so the attraction is getting stronger. So in general, we're always going to have an increasing effect, and actually this will normally be on the log scale, because each time it increases more and more and more. However, there's a bigger jump than normal between the shells, so we should see a kind of effect that looks something like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Again on the log scale, so these jumps are actually much bigger than they look. And this shows the one electron in the outer shell, and then there's a jump, and then we've got the 8 electrons in the next shell, and then there's another jump, and then we've got the 2 electrons in the next shell in. So successive ionization energies will always increase, and they normally increase in this way on a log scale, so these are actually going much, much, much higher. And we see significant jumps where there's a new shell, or where an electron is being removed from a shell that's closer to the nucleus. So this electron is being removed from a shell that's closer to the nucleus. And the same as this one. So there's different types of questions about this kind of thing, but when you're looking at successive ionization energies, they're normally asking you to identify an element, or identify the electron configuration of an element from information about its successive ionization energies. In the exam, when getting a question on one unit, could you answer part of the question with another unit? Yeah, I think that's true. You can. In the exam, you're expected to know all the stuff in your spec, but sometimes you may be the question might seem to be on one topic, but actually they're recalling questions or topics from another topic. So absolutely yes, you can answer a question with another unit. They're never just specifically on one, or they're rarely just specifically on one unless it's a multiple choice question.